So remember how we were talking about functions? So like functions, they take an input, like there's an argument, what's called an argument or a parameter like a, and they return some value. So in this case, in our most simple function, the parameter is x, and return y. And the thing to remember again is that y has to be the same type as the integer, as the function type. So in this case, y is an integer, the function type is an integer. The function itself, though, doesn't have to be the same type as the parameter. It's just in this case, example, because it's simple. So this kind of function is a regular function, but this kind of parameter, that int x, that's called a pass-by value. And so the thing to keep in mind with these pass-by values is that we're not sending in a, we're just sending in 5, which is the value of it. And so we're sending it into the function, we're going to do some calculation with it, and we're going to return y. But we're not, again, implicitly returning just y, the variable, we're returning the value that y has, which is 25. And so what's happening when we're calling this function here in main, we're sending in 5, and b is going, when this thing finishes out, b is going to be equal to 25, because that is what the function evaluates to. And so that is b as equal to 25. And so, how do we call a function main? Super important to remember that when we're calling a function, we don't name any types. We just pass in the variable a, and the function name, and that's it. And this is what's called a function call. It's called a function call because passing the value, we're expecting a return. Here we're going to take that function, which is going to be evaluated equal to some number when it's finished, and we're going to assign the values the function returns to b. And so the format that I want you guys to use in this class is prototype, int main, and then the name, and then how the function is actually implemented. And so the difference between a prototype and an implementation is the prototype just tells me type of the function, name of the function, type of the parameters, name of the parameter. And we can have an infinite number of parameters. Yeah. So let's try making like a very simple function. In this case, like write a function named check. That has 3 parameters. First parameter set an integer number, second, third parameter set doubles. Remember, so function parameters do not have to have the same type. They can be any types, and then the return statement could be any other type. Nothing has to match here, except the function type and the return type. Good. So when we set up a simple function, let's see. Okay, right. Simple function, we're going to do our usual. Let's set this function check, CP. And so we do our usual, right? Dot include iostream standard. And then the other thing we want to do, okay, so compute instruction set says that we should write a function. A function should have 3 parameters. So check, the parameter is an integer. And so this is what's called a simple display functions. Display functions don't return anything, they just print stuff out. So when a function doesn't return anything, we use a type called void. So we'll do void check int and 1, double, and 2, and okay, so int main. And what we're going to do now is called a stub. And what I mean by that is I'm going to just write an empty function then I'm going to write the function just down here. This is actual function implementation. So I'm going to do a double, right? And then I'm going to leave this empty. It doesn't return anything. And I'm just going to close the function up. And the reason I do is just to make sure that that my function matches the prototype. And so we'll compile this. Oh. And of course, there's a typo. So we'll fix that up. We'll compile. And we'll run check. And it's not going to do anything. But this is to show that it just compiles properly. Yeah. Sorry, my screen's being stupid right now. Okay. So now let's actually write in pieces. And so again, and so now, right, so all it's supposed to do is display the values. So that means that it's a cout, and 1 space and 2 space, and then 3, and then an N1. And so, and that's it. And I'm done implementing this function. There's really not much to it. And so, but like, how do I know I actually implement correctly? Well, we need to do a test. And this is why it's critical that you write good tests for your functions. So for one, we'll do, so we call the function check, and in this case, write 3 values, 2, 3.5, 4 because it's double, and 4.5 because it's another double. And that's all we need to call the function name, and the parameters that go into the function. So we'll close again, we'll compile, and we'll run that, and we'll run, and print out. And so here's an actually really important thing. Functions, you have to match the arguments to the types. So if I do this, it's not, let's see, right? I just changed it, so now I made the first argument, I was passing in a double. And so when I tried to compile, well, I compiled it, but what'll happen is it'll truncate because it passed with a double, it's a name. And this was this compiler being nice. Some compilers won't even run if I don't pass in the right type. I'll show you, let's actually show you an example of this. What if I tried to pass in a string? It won't let you because a string, it just doesn't know how to kind of convert a string to a double to a string. Okay, so that's one function. What if we want a little bit more complicated function? So the second method says let's write a program to compute a right triangle. Okay, so when we're adding another function, we can just add a function to the prototype. We're gonna make this case. Okay, so right triangles, everything can be doubles. We'll do double right triangle, double right a plus b, a squared plus b squared equals c squared. So let's do a double a and a double b. We like having, we again keep function names and parameter names very descriptive, because the more descriptive, the better. And again, we write the function. Spelling is super important. Double A, double B. I have to let it make it return something, or it's going to yell. So in this case, I'll have it return a double. Actually, let me get rid of that so you can see it yelling at you. But so we'll save. We save and we compile. And again, always do this. Every time you define a function, just make an empty one, which is again called a stub, compile it, check that like you didn't screw up anything with spelling or whatever, and then start filling it in, because the fewer moving pieces you have, the easier it is to figure out what went wrong. Okay, so we'll compile and it'll give a warning that you didn't return anything. So in this case, the second part of a stub is we have it return something that we just any value whatsoever. You know, it's just a basic value. We'll compile, and it compiles cleanly now. But our function doesn't do anything yet. So we'll actually make it. So it's, remember, it's returning a double. It's returning a third side of a right triangle. And remember that formula? And we'll often want comments that tell us like what's going on here. So C is equal to A squared plus B squared, which I can't find, plus okay, and we don't actually have to explicitly mention a B or a Y, even though we do it other times. We can just do return square root of power A to 2 plus power B to the 2. And this is another really important thing. You can call a function inside another function inside another function inside another function. There's like no rule against that. And it's not only built-in functions like these, which I need to include the math library to use, right? So let's do an include CMath. You might not be able to see it. Include CMath. But any custom one, like if I wanted to, I could call check in here and it would be just fine. Let's actually do that. Not for any. Yeah. So actually, what let's do is let's set double. Let's set C to this. Double C is equal to this. And the reason we do this, we're gonna call check inside here. So you could see that you can call one function inside another function. Again, we just pass in the parameters. And we'll do C. And we're going to return C because that's what we care about. And so again, we want to call the function, we want to check it. And so what's a typical triangle that we know, right triangle kind of thing that we know matches? 3, 4, 5, right? A 3, 4, 5 triangle. So one of the usual, so a sane check would be something like if 5 is equal to right triangle 3 and 4, then we've implemented it correctly or semi-correctly. If we were doing this like on a real for any like real code that is important, you'd want way more tests, but always have at least 1 or 8. So yeah. Let's see. Right, so we call check the 3, 4, 5 is when we call check inside by triangle, and it works fine. So that's a simple. Sorry about that. So that's a simple pass by simple, straightforward. All the parameters are passing in the numbers. Which actually, let me go back and explain what that's about there. So what we mean by pass by value is when in this case, we actually just passed values anyways, but like here, when we call check inside right triangle, we weren't passing A, we weren't passing B, we were passing 2, we were passing 3, we were passing 4, and then we were passing 5, and those numbers. And the reason I'm telling you this is because right now we're going to talk about what happens when you're not just passing values. So that's called pass by reference. And you guys see this little ampersand here when we do a pass by reference? That ampersand, you guys have hopefully this is looking a little bit familiar, right? Like the back of your heads, maybe. So the pass by reference ampersand, it looks like reference off of different pointers, right? And that's because it is a pointer. What we're saying is we're not going to pass you the value of y. No, we're going to pass you the address of the space in memory where y lives. So in this case, you see that we don't need to return anything. And the reason we don't return anything is because we're changing y in the function, and we're going to change the thing that is y along the way. So, well, here, we're going to call a function square. And this time we're going to pass in a and b. So we pass in a as a value because, like, the x has there's no ampersand, so the x is a pass by value. And that's a big thing. Like, we can mix pass by value and pass by reference. There's no, like, they all must be a pass by value, they all must be pass by reference. They can be both. And again, you can have about 100 parameters. It's going to look terrible, but your compiler probably won't complain. The other thing is, I kind of mentioned this is a and b, and this is x and y here. Remember, the names are arbitrary. These don't have to match those because they just get like in this case, that 5 gets passed along, and so x is 5, and it's going to get passed through. Now, here's the thing with b, and this is what's like the important drill into moment about pass by reference, is that we're not passing the value of b. We haven't actually initialized b, but even if we did, what we're passing along is the address to the place in memory for b. So a pointer to b. So we're going to pass along the whole, like, b. And so what happens here is, because it's a reference, y becomes just y basically becomes becomes a reference to b, or another name for b. So we're just going to chop it on. So now this is b and y. So when we change y in this function, and now set y is equal to 25, we write in that memory location 25. But that memory location isn't just y, it's also b. So when we come back here, we don't return anything because that function doesn't have return. And so if we would try to set a value equal to square, the value would have nothing to it. But instead, what happens is b has that value of 25 when we finished, because we changed b inside the function, because y and b were pointing to the same place in memory, or pointing to the same place in memory. Now, after we exit the function, y and x no longer exist because they only exist inside the function. But it's important to remember that because of the reference, b and y are the same, so any changes made to y inside the function are changes that affect b outside of the function once the function is exited. So again, we'll pass in 5, we'll pass in b, we'll set y to 25, and now b is 25. And that's called a pass by reference because of the reference operator, the ampersand, and because it's the memory reference. Okay. And so how do we use it? The same way we use any other function, we pass in the parameters. In this case, we don't assign any value. We don't assign the value to anything because square has a void type, so it doesn't return anything. And so instead, in this case, we're going to put the result in b, and so that's why we'll just print out b after we're done, because the result will be stored in b. Because b is y. Again, x is just the value. X is not a reference parameter; it's a value parameter. So whatever we input for a, that, like in this case, if we input 5, that x is going to be a 5 now. We're going to be setting the 5 here and 5. Okay, so let's do this function And so how are we going to make some sample function, right? Let's talk about add n. We'll add some value to an n for an input parameter, and then the user can set n, but it defaults to 0. Okay, so I'm going to actually change this name from check.cpp to func. And the reason for that is that I wanted to show you all that you can do multiple functions in one file. You can have 1.5 billion for all it matters. So in this case, int add n. So int n. So we're going to add n. We're actually not going to worry about the defaulting to 0 right now. So we're going to add n, and we're going to add it to an x in place. So we're going to set x as the reference parameter. Again, like always, we're going to just make a stub version of this to make sure that we didn't mess anything up. And I realized I'm not sharing the right window, which that would be a problem. Sorry about that. So again, as you can see up here, we made a little reference the prototype for add n, and then ampersand x. We're going to int add n, and then int ampersand x. And that's all. Oh, sorry, this isn't int, this is void, because again, in this case, we're not actually going to return anything. By the way, we could have a path by reference that does return something too, and often that'll be kind of an error code type deal, but don't worry about that too much for now. So x plus equal n, and that's it. And so we'll save, we'll compile. Again, we haven't actually done anything yet. And so now let's use our add n. So let's make an int. Let's assign x to 1, and int n is equal to 5. So what we'll do is we'll call add n with x with n and x. Oh, and this is really big, right? You see here when I call the function, I don't put an ampersand. You don't put an ampersand when you call a path by reference. That happens on the function side. It knows that it'll take the reference because of the ampersand in its declaration here. This is called the function declaration. So here you just pass in the variable. Well, and as usual, we should actually change this to factor, because again, names they are arbitrary. And so if we want to change the changes, we'll just see out num afterwards. And as you can see, it's kind of getting hard to remember what each of these functions are about. So that's why we're going to clean up these error messages. And after, let's print out what num is before we call the function. Okay, and so I should, okay. I don't even want this to be on the line, so we're not going to bother with that. And we're going to see out right angle. These days I'll remember to spell. So now we'll do a compilation again, and we'll call the function. And so these, they're not so interesting, but this is the interest part. Before we call that n, it was 1. And now after we call that n, x now becomes 6. And that's because it was passed in as a reference. So when we changed x inside the function by adding n to it, it propagated back to the function, because that the x inside the function is just another name for for a variable. Okay. So 0 is right. We had called num here. Num is 1. This num gets passed into the function. X becomes another name for the same place in memory as num. We add n to x, which means we added n to num. And so that's why num is 6 afterwards and it's 1 beforehand. So those are so pass by value and pass by reference are your two basic types of parameters. And they're the ones you'll be dealing with most. A good chunk of the time you'll be dealing with pass by value, but most complex data types are passed by reference, so it's good to keep that in mind while working with them. Okay. So sometimes we have these parameters, and we want to do what are called default always. The idea here is that we know what our parameters is. That sometimes we know what value we want to send in, or we'll ask the user for a parameter, but maybe we don't always care. Maybe we just want to. Maybe we have that just what's called. Oh, let me rephrase this. Let's take add an example here, a square root example. Let's say we don't want to we'll call square root, but we want sometimes I want it if I call square root with no argument, just return 0. So that's what a default thing is for. Or like in our add n, I sometimes don't want to pass n. I just want to use it. I don't want to pass n. I just want to. Oh man, I'm losing mine. I don't want to pass. I want to pass n, but sometimes I'm just like, okay, but default to 0. So if I don't pass an n, I'll just pass an x. I don't do anything because the add n by default will be 0. So that's the point of default always, is when that, we don't always, is that we want to give users the chance to control these things, but we also want to just set some basics in case the users don't care. So it works the same way. You'll name the function, you'll put your default argument, you can call the function, and if you don't call it with anything, that's just what happens. So the big rule though with defaults is that they have to come after regular arguments. We're not allowed to do defaults before regular arguments. So let's do modify checks so the right value defaults to 42. So let's give, okay. Okay, let's pull this up. Avoid check D. And then now check the int. I'm going to int 1. These are required to enter n1, but n2 is going to be 87, and double n3 is going to be equal to 42. We can have any number of defaults come after our non-default. And the code's exactly the same. So I'm just going to copy and paste in this case. Or actually what I'm going to do, because you're allowed to, and I have no problem with this, is check D. So what we're going to do is we're going to check D, and again, same as the parameter, int n1 double n2 is equal to double n2 is equal to 87. You might be able to get away with doing this only in one place, double n3. is equal to 42. And since I already have check written and it does what I want, I'm just going to call check with n1, n2, and n3. And so let's do a check, and let's do a check D. So check D where we only pass 1 and 2, and a check D where we only pass 0, 2, and only a 0. Okay. And it probably doesn't. Okay. So you can't do default argument unless you do this F permissive switch, which is the other reason why we won't really use them in class. Okay. And these are all warnings, not errors. So it'll still compile anyways. And so you'll see, right? We first time when we call it, because we're casting two arguments, we only get 42. Second time we call it 08742 because we're only passing one argument. The thing to know, oh, and there's the other thing. If I did a check D and I did 026, it wouldn't print out any of the defaults. In this case, it's 026. The other thing to know with defaults is that they take an end-to-end approach. Like the reason why you have to do it after the required arguments is because C++ arguments are called positional. So first argument matches the first thing, second argument matches the second thing, third to the third thing. So as you leave things out, we take the default starting from the end and filling back. So that's why it's the 87 and then 42. In this case, when we pass the 0 and 2, 42 is what prints. Okay. So those are default dogs. Now, next thing's right, we did this check and then a check B. We can also do what's called overloading. We can have two, we can actually name them both check. It would just be weird and confused. Actually, scratch that. We can't name both of them check because they have the both same number of arguments. What we could do though is if we decided one check took integers and we wanted another check that took doubles, we could do what's called overloading so that one function only took integers and one only took doubles, and one returned ints and one returned doubles. This isn't a big deal with wasn't really a big deal with integers, but it's a huge deal with that, like say our square function here, because if I try to pass a double into my int square, well, let's see what happens. Well, I'll show you what happens. Let's actually make I'm gonna write a new piece of code for this because it's cleaner. Sorry, I forgot. Okay, so we'll do our square, right? So int square, this is square. It takes a, it'll return a squared. And we don't need to like fix this. Close, return 0. And int square int a. And x. Well, in this case, this was x times x. Close. Compile again. That's 2. And then square, that's a p. The dash show, and I use Python apparently. No, wait. You are right, and this is wrong. Okay, so we'll run it. And I knew that I was wrong, by the way, because my error message, it said line 2 was blocked. So just went and fixed that line. It even said what was wrong, right? Because it gave me this count hash key. Okay, so we'll run this. And it was empty, right? Because we didn't actually do anything in it. So, right, if I do the first one, see out, what's it called? So if I call square with 2, it'll print out what I expect, right? But the question is, what happens when I call square with 2.5? And again, one of these days I'll spell things right. The error message, and again, I knew this because the error message said square was not declared in the scope, and from that I can see, oh, I probably just spelled it wrong. We'll compile and we'll run it, and it's 4 and 4, and you're totally like, wait, what? You sent in 2.5. Well, that's a problem with an integer function. Even if you don't send an integer, it'll just truncate to an integer, and so it'll get your answer as an integer. And so the simple answer to this is what's called overloading. And overloading says, I'm going to take the same function name, but I'm going to change either the types or number of parameters. We'll get to the second type later, so that I can have this function behave correctly. And so how do we overload square? We just make another version. We say, hey, if you're going to do a double, return a double. And so we're going to take in a double. And the function is going to look the same. X. And again, we're going to just return x times x. And we'll run. And see, now we'll get the right answer. Because now when the compiler sees that 2.5 double, it knows, hey, I'm going to go look for the 2.5. I'm going to go look for the one with the double, rather than just the one with the single. Sorry, I'm going to look for double type rather than the one that is an integer type. Okay. Okay, and so you can do that. You can also overload based on parameter count. So if you want one function that only takes in 2 arguments, and one that only takes in 3, and one that takes in 4 and 5 and whatever. But in those situations, I would often suggest that you're probably better off with in those suggestions, though, I would suggest that you should just use parameters. Not default parameters, or we need a redesign altogether, because it's very rare that you should be overloading the same function depending on how many arguments you're passing to it. So that's the old overloading, right? But this can kind of get cumbersome. Do you really want to have to write 2 or 3 functions just to have it deal with different types? Probably not. And so that's where templates come in. Templates are fantastic and confusing, but what their deal really is that they're saying is that, hey, compiler, I don't want to name types. I want you to do the work for me and kind of write code for me on the fly. And this is what a lot of modern C++ looks like, is this kind of, I'm going to kind of define these templates, and then you're going to just make the function for me. And so this template says, hey, take a function, take stuff of this argument type t. T is either a primitive data type like int or float or whatever, or something more complex. Take a function that takes in that parameter, and then I'm going to assign the function y to the same type, and I'm going to return y of that type t. And so what this translates to and then what will happen is the compiler will just generate the real function on the fly. And so what's important to consider here is that these functions don't have a prototype because this T templating is the function prototype. It's not a real function. It's just something the compiler uses to fill in the real function later. And templates can be passed by value and passed by reference. They don't can have parameters that are passed by value, passed by reference, and it can have default parameters, and like, except for the type thing, it works the same way as any other function. So let's copy a little square function, and let's make a template version. So square t.cpp. And I need to screen share my working notebook with you again, right? Okay, so jet. Okay, so like I was saying, there's no prototype. There's no implementation. So what happens is we declare the entire function before main, and it's, remember how this. Okay, so it's template class T. This thing is gonna, in this case, our function is gonna return type T. It's gonna also take in type T x, and I'm gonna simplify here. I'm just gonna return x times x. Okay. So again, we'll compile square. This thing is spelled wrong. Compile square T and run it. And when we run it, you guys see, works the same way as our non-templated function. It's just instead of having to do to overloaded type, we essentially let the compiler do the overloading by letting it figure out kind of by letting it substitute the type for T. And so this actually can do very weird things because C++ is what's called loosely typed. So what that means is I can do something like this. I can take the square root of A. And it'll compile perfectly. And it'll give me a nonsense answer. Because what's happening is it's taking the ASCII value of A, it's squaring that, and then it's returning the ASCII value of the square root of A. So we can, the ASCII value of A squared. So if we instead take something really early on the ASCII table, sorry, jet squared. So A is kind of far along in the ASCII table. We take something really early. I'm gonna just look it up a quick second. Sorry about this. I know you're not seeing anything because the screen cap's on. Let's do one thing at a time. So okay. Exclamation points are pretty early and appear to be pretty early in the ASCII table. The first bunch are what are called non-principals. Okay, so let's do. Okay, sorry. So let's do a space. What's the square root of? What's a space squared? So we'll compile again, and a space squared is apparently a space. So the weirdness behind this is that C++ is what's called a statically loosely typed value. Okay, so the square root, so a exclamation point squared is a large capital A. This is because C++ is, again, is what's called a static, weakly static type. What I mean by that is a static type is that we have two declaration statements. You have to tell the computer, hey, I need you to carve out this much space for my variable. And I'm going to slow there. But what I mean by weakly typed is that C++ will kind of treat anything, is that it'll do things like try to multiply, like it'll take a character, it'll find it can take a character and treat it as an integer and treat it as a integer and take a double and truncate as an integer and do all this stuff without explicitly telling you. And the reason for that is like it just looks at the space involved. And this is, by the way, something that can end up biting you. So be very careful when you're working with like weird C++ types that you're paying attention to what types you're sending in and what types you expect back, because C++ won't do any sanity checking for you. But the point here is that the flexibility of templates is that the flexibility of templates, though, is that you can get the square of a character because it'll just pipe it in. Okay, let's go back to the lecture. Okay, so that's templates. Templates don't have to be limited to one type. We could have a type 1 and a type 2. They don't have to match. The type 1 and type 2 are totally arbitrary, by the way. The compilers and what I mean by that is, sorry, T1 and T2 and T, they're arbitrary. They're a convention. You can name these things data type 1, data type 2. You can name them kitty 1, kitty 2. But people are expecting type 1 and type 2, and so anybody else has to read your code, that's, it's kind of do them a favor. Use the convention and it'll be much simpler. So in this case, we're passing in square two variables of two different types. They could end up being the same type because it's just a substitution thing. And the function doesn't have to turn a templated type. Okay, that's for reference. So actually, let me show you this, because this will show you overloading of parameters. So let's do a square t. So we're going to make a separate template. Template class t1, class t2. In this case, our function is void. Remember, a template can return a type t. It can also return a type void. It can also be a void type. It can also be an integer, a double, or whatever. Templates, again, work the same as any other functions. And so let's do a path by reference on 2. And y is just equal to x squared. And we'll close. And we can call this function the same way we would call anything else. But in this case, I'm going to just do... Okay, in this case, y is an integer. And so we'll call square on 2.5. 2.5 and y, and we'll see out y 5 and y. In this case, let's call out square with a 2. Oh, and now let's make, sorry, w. Let's make this a v. So v. And a double y. W and plus w. We can pass this in 2.5 again. And we'll again see out 5. W. We'll compile this. I did double W, C out W. Oh, sorry, this was V. V, compile. And we'll run it. And you see, right? Oh, let me actually, yeah, I forgot an inline somewhere, and that makes it hard to read. See, we like an inline file. So, like, and so we'll see here, we sent in a 2.5 and the y is a 6 because, like, sorry, two things are going on here. For one, we're doing this parameter overloading. The first time we called this, this goes into the square that has only one parameter. And the second time we call this, it goes into a square that has the x and the y. And because this Go compiler knows, okay, I got to match up types and I got to match up parameter count. We're doing this parameter overloading with templates. You can also do it with in non-templated functions. Works the same. Based overloading. And now the second thing that's happening is the first time we do this, we sent in y is integer, and so the answer is an integer because it gets truncated. And the second time we sent this in, we were like, okay, but let's keep y a double, and so it squared it and then left y a double and didn't try to truncate, because, and again, this is just like we're taking advantage of, you know, templating and the whole deal with templates, which is that you can just grab that it'll figure out all the typing for you, because otherwise, like if you wanted to have all your bases covered for every type, we would need, let's see, we really want an integer, a double, and a float version, so 3 here, and then integer, double, float, and every variation. So we're looking at like 3 to 6 to 9, so I don't even know how many overloaded here. You know, so that's like 6 to 12 functions that we can instead combine in 2 because of templates. So they're immensely powerful for essentially abstracting out your data type. Okay. Okay. Because we're talking about this, right? So that's what we use functions. Okay, so the other thing to keep in mind with functions is something called scope, and we've kind of touched on this before, right? That the deal behind scope is that you're essentially almost making a little black box around your function, that any variable you define inside your function only exists in this little world of your function. And once you've exited from your function, nothing in the function ceases to exist. It's like an iron curtain has dropped down. Function is off on its own little planet. So that's what's called local scope. That local scope is kind of the stuff inside any variable declared inside a base, anything inside the base, it is only exists within those bases, only exists inside that function, inside the statement, whatever. And so it's only seen in function as defined, and the name can be, and what this really means also is that the name can be reused in other functions, like you guys just saw with our square. Right, with our square here, I can use x here and I can use x again here, and they don't conflict with each other at all because they each exist in their own scope. In this case, this x is inside this function square, this function scope, and this x squared is inside this function scope. So they're completely independent of each other, essentially. And so that's what local scope is about. And neither of these x's or these y's have anything to do with its name. So if I put another x or y here, it would have its own values and its own numbers and not be at all related to anything going on here unless it was passed in as a reference, like passed in as the y here for the reference parameter. So what an example of this, because I have to have one. So I can do a double y. So here's an interesting thing. I can do a double y in x here and set my double y equals 5 int x, and then call square. And I can call square with yx, right, which is the reverse of what we've been doing. The don't do this, and like, I don't recommend you doing this because it'll probably confuse anybody reading your code, but this is a proof of concept. What I want you to get out of this is that, X and Y, the names didn't matter. I may have called it X, but when I passed it in, the X that I passed in here is a wholly independent X from this local X or this local Y. So I pass in that location, the memory location, to that X that's labeled X, and it gets this Y label thrown on it too. This X is associated with a totally different memory location that has the value that I passed in, this 5. It has we pass in that 5, and this X in that function, it points to a memory location that has a value of 5 in it. Whereas this X that I passed in from what's called the main scope has its memory location also this Y attaches to its memory location, and so now when I change this Y, that X gets changed. But yeah, the big thing is that this X and Y are completely separate entities from the X and Y setup function. And again, these X and Y is totally separate from these, separate from those. They won't, like, separate worlds. Okay. So this is important to keep in mind because, so that's your local scope that, it only exists inside itself. Now, there's nothing called global scope. Global scope is bad. I'm not even going to show you how to do it because it's terrible practice, and you guys will not be writing anything where you ever need to use global scope, and it breaks things. But global scope is just when I define a variable outside int main. So what I define by using namespace standard, and I define all my prototypes. So if I would do an int x there, int y there, or whatever, it would be here, I'll show you. I'll show you how to do this, but don't ever do this. So if I wanted to make a global x and a global y, I would do something like int x and int y. Now here's the problem with this. Because it's global, every x and y in here has to do with this x and y. And that can get very, very weird when you're trying to, when you have multiple programs, multiple functions changing it, figuring out what it is at the end. And of course, I didn't show the right screen. Yep. This is how you do global. I defined an x and y before, and it's like something like 5 and something like 6. And so what happens is, the problem with this really is that it's hard to keep track of what the value of x and y are when you define it globally, because every change to it changes it, and so you have to kind of keep track of all of these concurrent processes, and so it gets really confusing when you have multiple functions talking to multiple functions and multiple programs talking to the same piece of code, and changing that x and that y. For multiple functions even. So we'll compile again and we'll run it. And in this case, it didn't do anything terrible because we weren't changing. Because we never really changed that x and y. Or we changed it, but we would recreate and overwrite it. But yeah, that's a global. Oh, so actually, let me show you another way to do it. So let's make this a global int a. So what I mean by global is here we'll see out a. See out a. We'll see out a here. See out. ignore the thing there. Okay. So, and we don't define the global inside either of these functions because it's assigned there. But right, let's keep changing a. So a is equal to 1. Plus equal 2. A plus equal 3. Oh, and let's actually make this even more annoying. So we're going to change a inside all these functions too. So a is going to get changed all over the place. Okay. And we'll run it, and you'll see the value of a is just going to jump all over, right? 0, 1, 3, 11, 20, 28. And that's because every single time we call a function that uses a, every time is because this is that whole a is global, so every change to a actually propagates through. And so the reason you don't use global variables is because it's going to be really hard to predict what the end value of a is, in this case, because you've kept changing it. And the bigger thing is because, say, you have two functions and the functions have an a variable named a inside them, well, that will conflict with your a, global a, and then bad things could happen. So, yeah. If we want to actually keep track of this, right, so our first a was 1, then we subtracted 1, so then it was 0, then we added 2, and then we subtracted 1, which is why the second a is 1, onwards, onwards. Okay. Okay. So those are your scopes. The other thing is how are variables actually stored in memory? We kind of sort of talked about this back when so we've discussed this before. That variables that we take a place in memory, we carve out enough of a chunk and we just carve out a little piece for our whichever variable we're defining here, that like int, double or float. So there are three main types. Auto is the default, so that's why you never write it. So just when you're doing int var1, you're doing auto, and what's happening here is like your program compiles, and when it compiles, it creates just a table. Okay, so you have integer, you need space here when you need, so with your compiles is going to kind of have a list of, okay, so you need this much space and this much space and this much space, but it doesn't actually give you this space until you run the .exe. So it's kind of like ordering food. So your waiter is taking down the menu, but he only gives it to the chef when you're like, okay, ready. So he'll send it in, and then you'll get the space. Static is that when we actually compile, we don't just take down, oh, we need this much space, that much space. We actually like, okay, inch drop, carve out space for an inch. Okay, float, carve out space for an float, etc. Generally, you want to use auto. The time when it's worth it to do static is when you're working with really huge files and you don't quite know how much space it's going to take. And the reason for that is if you're afraid your memory is going to crash, you want to know that on compilation rather than when you try to execute, right? Because the last thing you want to happen, and this happened to me more than once, is go 2-3 days into a job and then have things crash because of memory errors. So those are, but those are trade-offs because auto is usually much more efficient. And then there's extern, and extern is, you can have auto and static extern, but the deal with an extern is that like I'm writing a function, and I'm writing a variable, I'm writing a function, and I want it to be seen in by code outside of my C++ file, or like, and not even something I can like just code outside of my little library, like all the way outside. So then I'll name an extern so that that code can see it. You'll tend to use something like extern if you're writing something where you wrote a little C++ library, now you need some like C or MATLAB or something that's not C++ code to see it, or if like you've compiled your library and you're giving this compiled library to someone and they want to call your code, then it also needs to be extern. Okay, so that's it for functions. There's a quiz Thursday. It'll be on really basic stuff, right? Know pass by value, know what a basic function is and how it works, know how pass by value parameters work, know how pass by reference parameters work, and know the basics of templates. Okay, and remember, won't be here Wednesday, won't be here Thursday, but you're required to show up. Thanks.